All righty. First page. Go to the first page. There we go. So today we are going to talk about the differential pair amplifier. Get self-situated. Let's say that we have the following circuit. My pen will write. All right. So this is our Mosfet differential pair amplifier. We can see that at the most basic level, it has two inputs, VN1 and VN2, applied at the gates of transistors M1 and M2 respectively. And we also have two outputs, Vout1 and Vout2, which is taken at the drain of transistors M1 and M2. So this is a differential amplifier. So the difference between VN1 and VN2, and amplifies it at the output, which is Vout1 minus Vout2. This circuit is one that requires balance for proper operation, so it's very critical that the resistors and the MOSFETs are matched, meaning that they're of the same size and things like that. So if we were to look at this guy as a DC circuit where we're making a couple of simple alterations, so let's say, for the sake of argument, that I grounded both of my input terminals. I could see that there's going to be some current ID1, and let me draw this better. It's going to get sunk by our reference current source at the bottom, and there's similarly a current ID2 that gets sunk in the bottom there. And we can use Kirchhoff's current law to find that our drain current ID1 plus our drain current ID2 must be equal to our bias current. We cannot avoid this fact. When the aspect ratio of transistor M1 is equal to the aspect ratio of transistor 2 and our resistors RD1 and RD2 are equal, this means, should be intuitively obvious, that our drain current ID1 and our drain current ID2 are equal, and they are each exactly 1/2 of our bias current. And again, this is under the supposition that our voltage VN1 and VN2 are still grounded or identical, really. So if we assume that both transistors are operating in saturation, where ID is equal to 1/2 mu E C aux W over L times VGS minus VTH squared. Since the drain current for both transistors is established by the ideal current source and the gate voltage is fixed at 0 volts. This means that the voltage present at the source will settle to whatever value creates a VGS corresponding to a drain current of I bias over 2. And we'll explore this in just a moment. Also, since the current through each branch is fixed, the output voltages V1 or Vout1 and Vout2 are determined as Vout is equal to VDD minus ID times RD is equal to VDD minus 1/2 I bias RD. So let's see. All right, so this is something I was playing around with this morning, and I have made a simple differential Mosfet amplifier circuit. And let me edit this to where this is simply actually grounded. So I have the circuit that we have drawn, right? The only real difference here is that I have explicitly tied the body of each of my transistors to not ground, but the source. And we might have to explore that in a moment. But right now, the body and the source are at the same potential because that's going to hopefully eliminate any body effects that we might have. So I have this guy set up to do a simple transient analysis that ends at 5 milliseconds, which, since this is a DC circuit, should be giving me simple straight lines. So if I run my simulation, we can observe that Vout1 is exactly 4 volts. And this is important. We'll talk about it in a minute. Vout2 is also exactly 4 volts. So nothing wild or crazy there. If our differential input signal is 0, then the difference in our outputs should also be 0. And we can also look and see that the voltage at our source, in this case, is negative 1.4 volts. So that is a little bit interesting to me, because that's a little bit lower than I would have expected. And so what I mean by that, this is going to get confusing me. Let me share my other screen again. So with our transistor operating in saturation, we should expect that the voltage present at our source should be approximately 0 volts minus our threshold voltage for our NMOS transistors plus VDS sat. So really we are expecting this the source voltage to settle on a value where the transistor is just barely in saturation, right? We shouldn't be hitting deep saturation or anything like that. But I'm willing to bet, actually, we'll check that in a second. So this would be approximately equal to negative 0.7 volts plus 0.25 volts, should give us something in the ballpark of negative 0.95. Now what I want to see here is what's going to happen if we change our drain current here from 40 micro to 20 micro, which is the reference current that we are used to having. Because I have these transistors set up. Oh, actually, they don't have a length or width. That may be the issue here. 10 by 2. And let's move this back to 40. All right, let's see what happens. So it's even worse now. It's negative 2.157 volts. So that's not good. So let's see what happens when we drop this guy to 20. Negative 1.7. This is not behaving exactly in the way that I would expect. 10. Oh, it's backwards. All right, sorry, having technical difficulties this morning. For whatever reason, LT Spice does length and then width, not width and then length. There we go. Okay, so we're hitting negative 900 millivolts, which is actually pretty close to what our expected value was. Let me see what we get when this guy jumps up to 40 microns, just to see. 971 millivolts, so a little bit closer. So things are behaving how they're supposed to when I actually put stuff in the computer right. Who would have thunk it? All right. And just for the sake of argument, let's look at what our expected output voltage should be as well, right? So our output voltage, V out, should be VDD, which is 5 volts, minus 1/2 of our 40 microamps reference current multiplied by our drain resistor, which was 50 kiloohms. And this should give us 4 volts. So our model is pretty dang good at describing what's going on here. So, all right. Now, for this guy to work properly, both transistors need to be in saturation. So, to ensure that, oh goodness, where'd my page go? I guess I'm just running out of room here. The transistors stay in saturation. The drain voltage with respect to the source, VDS, must always be higher Then the gate voltage, VGS, minus the threshold voltage. Or VDS, come on pen, there we go, is greater than or equal to VGS minus VTHN, which implies then that our gate drain voltage, VGD, has to be less than or equal to VTHN. Since our drain voltage is fixed, this restricts the values that we can apply to the gate of each transistor. Which, if you'll recall, are our input voltages. So our common mode voltage cannot exceed V out plus VTHN is about 4.7 volts for our example. With the 40 microamp biasing current, 50 kilo ohm resistance. Otherwise, the transistors will enter the triode region. And in the triode region, effectively, both of the transistors would act, depending on how deep they were, like resistors themselves. Okay, so one of the biggest benefits of a differential pair amplifier is that it suppresses common mode signals. This is called the common mode rejection. Differential pair amplifiers suppress common mode signals. Okay. So we saw that when we have 0 volts at both inputs, there is no difference in our output. Now, let's see what happens if instead of having 0 volts at each input, we put 1 volt at each input, right? So we see that our source voltage, VSS, has changed, which makes perfect sense because, again, it's just going to adapt to whatever it needs to be. Let's look now at our output voltage. Well, it's still exactly 4 volts for Vout1, and it's still exactly 4 volts for Vout2. And the reason is because we have a balanced system, right? So if both sides of our circuit are identical, exactly half of our bias current is going to flow through each one. If we change this guy to 2 volts and 2 volts, again, they're both sitting at exactly 4 volts. We're running into a little bit of decrease in the current or in the voltage for some reason. So I'm not sure why that's varying with time, other than we might be pushing on the edge of triode or something like that. Our source voltage is way down here at approximately positive 1 volts. So we're so it's about 0.95 below this. Anyway, so we can see that our common mode signal, or whatever amount of voltage is common to both inputs, gets rejected. But if we change things slightly, so let's put 0 volts back here. Actually, hold on, let's put 0 volts on V2, VN2, and let's change this guy. Instead of having a 0 volt signal, let's put a sinusoid. Let's make it a very tiny sinusoid, 1 millivolt, and let's do a frequency of 1 kilohertz, no DC offset, and let's see what happens. Why are we getting, this is not remotely what I was expecting. Let me see something here. Why are you not behaving today? 1 millivolt, 1 kilohertz, no DC offset. So what I'm expecting to see is that I should be getting a sinusoid at my output. Why is this behaving poorly? Got Vout1 and Vout2 measured. Why am I just getting a voltage pulse of 1.1 kilovolts at my output? That doesn't make any sense. This shouldn't change anything, it doesn't. Oh, why are you being difficult? Let's see what happens if I lower the frequency. Still being weird.
Do you think it would change if you, never mind, I see you just did something, never mind.
Yeah, so I just changed, I put a 1 volt DC offset on both sides. and it's still behaving poorly, which is confusing the bejesus out of me, because when I did it before class, I did see the signal. So the only thing I can think of here, all right. So this is expecting, I bet actually this is what it is. So right now, effectively, I have this guy saying that it is 2 meters and 10 meters, I think, long. So I didn't put dimension units. All right. So our length of 2 lambda would be the same as 0.6 microns, and this would be 3 microns. Let me see if this fixes it, putting in the actual dimensions instead of putting it in terms of how many grid units. There we go. All right, so I had my transistors impossibly large and it didn't care for that. When I actually put them in the physical dimensions, they will actually occupy. That's one of the problems, at least that I struggle with, obviously, is the fact that electric wants everything in terms of grid units, and LT Spice wants everything in terms of the physical dimensions of the device. So I apologize for that, but now everything's working pretty okay. So what we see here, or what I have been attempting to illustrate, is that we have what's called a differential gain going on. So as soon as there's a difference in the input signal, we get some form of amplification. So how can we determine the amount of amplification that we have? What I'm going to do is, instead of having V out 1 and V out 2, I am going to add V out 1 minus V out 2. And now it should be fairly easy to see what's going on, but I'll go ahead and add this trace as well. So I want let's see, trying to figure out what this node is. I'm going to label this node right here as simply VN1. And on the other side, I'm going to define this node as VN2. And now I can add my trace that is simply VN1 minus VN2. And I see that I have a differential gain, okay? So what is my gain here?
About a millivolt, or maybe half a millivolt because of the...
So the blue curve is my input signal and the green curve is my output signal.
Oh, sorry. It's like 6, like a gain of 6 or something like that.
Yeah, well, I would argue it's a little closer to 7, but yeah, somewhere between 6 and 7. Actually, somewhere between -6 and -7, because whenever my differential input signal goes low, my output signal, so whenever my differential input signal is negative, my output signal is positive, and vice versa. But we have introduced a small amount of gain. And actually it's looking like, so if we look over here at closer to 5 milliseconds, it's actually hitting right on 7. So what I'm going to do is change my simulation command a little bit, because the awkwardness that we might be seeing is potentially due to transient conditions, because we're starting those DC signals up. instantaneously. So let's look at this over 25 milliseconds. That's still gradually increasing. So I would say, let's call it a little under 7 for our differential input signal, our differential output signal. So our input signal is well behaved. I'm not sure why the last cycle or two is showing a gain of almost exactly 7. Because after 25 oscillations, I would figure that this would be behaving as effectively sinusoidal steady state, but it doesn't quite appear to be. So, all right, so we have a differential gain, V out divided by V in, of approximately -7. So let's talk about why this happens. All right, so we need to remember 2 things. All right, so to understand the differential amplifier circuit's ability to amplify the differential voltage Bn1 minus Bn2, we must remember following items. Number 1, the sum of our drain currents must always be equal to our bias current. And number 2, the source voltage for transistor M1 has to be the same as the source voltage for transistor M2, and it's because the sources are tied together. So, if the gate of M1, if the gate voltage of M1 is higher than the gate voltage of M2, then VGS1 must also be higher. And stop cutting out on me. Than the voltage VGS2. So what does this mean? If VGS1 is larger than VGS2 and our transistor is in saturation, we come back here, what does it mean for the drain current of transistor 1? So if this guy increases, what happens to the drain current?
It goes up as well.
Exactly. So that means M1 is going to have a larger current flowing through it than M2. If the drain current M1 increases, what does the drain current through M2 have to do?
Decrease to keep
It
the
has to
balance.
decrease. Exactly, because the sum of those drain currents must be equal to our bias current. So if ID1 goes up, ID2 has to lower by an equal amount. This is exactly why we get that negative gain, right? So let's see, these changes. In drain currents. Then create a differential output voltage. To occur. All right, so we have the basics of the differential amplifier down. Now, let's take things one step further. Instead of using resistors to load our amplifier, let's use a active Pmos load. So an active Pmos current mirror to drive this guy. No. The reasons for doing this are twofold. We have our Pmos transistors. Here is our NMOS transistor. So this guy is M1, where we apply VN1. This guy is M3 over here. We have transistor M2. We apply VN2, which means this guy is going to be M4. Here is our reference current. I bias, and we're going to do one thing here. So our ultimate goal in this class is to design an op-amp, okay? So if we go way back up here to the beginning, this differential amplifier is actually really close to what we would expect of an op-amp, right? In its most basic form, an op-amp has a non-inverting terminal and an inverting terminal and an output terminal. And what should happen, at least in an open loop configuration, is that that differential input signal gets amplified and we're able to measure the output. Now, right now, with the current configuration that we have two output signals, one for each corresponding input pin. This Pmos active load allows us to get a single output signal. So what we have is a Pmos current mirror on top and the basics of our differential amplifier on the bottom. Okay, I'll go to the next page. So the bottom half of the new differential pair is identical to our previous examples. Now we have on pen thingy, a Pmos current mirror replacing our resistors. The output voltage of this circuit is dependent on the current supplied by the Pmos current mirror. Let's see, and what I addressed momentarily ago, or a moment ago. So you may have noticed that the output voltage the out one has disappeared. We now have a single, Not how you spell single. Single-ended output. Which is a common topology used in a wide range of applications. All right. So let's see, let's pop into LT Spice here. Share. LT Spice. And I get rid of those resistors. Let me move these guys up here for now, out of the way. So I'm going to put some Pmos transistors in. All right, so let's see. 1, 2. Pmos 4. And I'm going to hit Control E. There's M4. Wire back. And let's just re-put them on. VDD. VDD. I need to tie those two guys together. That. Here's my output voltage, V out. All right, I need to tie my body of my Pmos transistors to VDD. And I need to set the physical dimensions of my Pmos transistors. So let's see, the length is still going to be 2, so that's 0.6 microns. I think we've been using 30 by 2 Pmos transistors. So that would be 30 times 0.3 nanometers would be 9 microns. Yeah. Okay. And let's hope this works. So we have a signal. Let me change my analysis edit simulation command. Let's do it over 5 milliseconds again. So it's centered around 3.8 3.880 volts. So what I'm about to do, I'm going to add .88 volts plus VN1 minus VN2. So all I'm doing here is I'm putting a DC offset onto the difference of our input signals so that we can see what our gain is. Okay. So that effectively we have the things on the exact same scale. So if we put in a 1 millivolt signal, let's see if I left click on V out and I drag this over to a peak, right? So you guys can't see this, so let me move it over. Okay. So we get 3.902, or 3.90285. Actually, a better way to do this. Let me change this. So instead of adding the DC offset, I'm going to subtract the DC offset of 3.880 volts here. All right, now it's a little bit easier to see what's going on. All right, so here is 0.1. So for a 1 volt or 1 millivolt differential input signal, we get a 22.85 millivolt output signal. So our gain has increased by an extra factor of 3 here, okay? So it was 7 with the resistor biasing, and now it's up to close to 23 with the Pmos biasing. So we have definitely increased our differential gain. Let's talk about why. So when we simulated our circuit, we saw that our differential gain increased from around 7 to around 22, 23. This is due to the increase in the output resistance of our circuit. So our small signal model on the output side kind of just looks like this, right? So we have VDD. Here's our Pmos transistor. We have this resistance RO4, which is due to channel length modulation. Here's our output voltage V out. Sorry, this should be 2 because this is transistor. M2. So our output resistance that we have, hopefully it's pretty easy to see for our small signal model, is just going to be RO2 in parallel with RO4. And so our differential gain is going to be our transconductance for transistor 1 or 2, because they're identical, multiplied by R out 2 in parallel with R out 4. All right, so let's take a 5-minute break, and then when we get back, we'll start laying this guy out in electric. All righty, I've remembered to unmute myself, and I've remembered to share my screen. So I am going to go into Explorer. I want to open my 438.211 JLib file. I went through and I resized my grounding ring for my current mirror just because I thought I could get away with it, and I was right by remembering to put in that NWell region. It's not remotely important that you guys do it. I just wanted it to be the same, that grounding ring or the guard ring around the Pmos transistor to be of the same size, because I'm weird and it bothered me that it wasn't the same size. Right now, I'm going to create a new cell, and let's call this Differential Amplifier. And gonna get to work. So let's see, we have an NMOS transistor. I've been rotating all of them, so if I rotate one, I should rotate literally all of them. This is going to be 10 by 2. I'm going to rotate it 90 degrees. And to make my life easier when we do simulations and stuff, I'm going to name this guy transistor M1. I'm going to attempt to select that text. I'm going to rotate my text, make it slightly larger, and I'm also going to move it. See that in a moment. I'm going to put it over there. Now with my transistor selected, I can set my spice model. It's going to be NMOS. And I'm going to rotate this as well. All right, and let's see, I'm going to have another one of these guys. So I'm just going to simply copy, Control-C, and paste over here. And it automatically updated that to be transistor M2, which is great. That's what I was hoping it would do. My sources are tied together. So I'm going to make a contact here, which needs to be 5 in the X direction, 10 in the Y direction, and tie the active regions together. Can I get it closer? No, there's where I should have it. All right. And I'm going to put a label here in the middle that's letting you know that this is the, no, that's not what I wanted. Control, left click, control, left click, control, control. Finally have the text selected. This is the source of transistors M1 and 2. Making my drain for transistor M1. And now I'm going to make the drain for transistor M2. All right, so our sources are tied together by definition. Our drains are not, our gates aren't tied to anything, so this is looking pretty good here. The only thing I'm currently considering is whether or not I want to put a guard ring around this guy. And the reason I'm undecided is because this source isn't tied to ground, right? In our circuit simulation where everything was working pretty well, our body connection was tied explicitly to our source. Let me show you guys just real quick. So if we look at our LT Spice schematic diagram here, this is our body connection and it is tied explicitly to our source. Same on both sides here, and it seems to be behaving pretty well. I want to see, just for the heck of it, what happens if I tie those body connections explicitly to ground, if that changes my gain or anything. My best guess is that it will have an effect, because if my source and body aren't at the same potential, then I should see body effects, which causes an increase in my threshold voltage and all that kind of good stuff. So let's just see. My gain still appears to be approximately 22 to 23. So it really didn't have a whole heck of a lot of an effect. All right. So that means I'm going to carry on with putting a guard ring there, just because it's good practice. All right, so let's see. I need to connect to the P well. And let's make this 20. Let's see how close I can get without causing an error. Still no errors. This is saying it's going to give me an error. Let's see. Okay, it does give me an error. Still errors. No errors. That might not be large enough though. Let's make that 25. And for the one that's going to go across, let's just ballpark it at 40 for right now. That actually seems pretty reasonable. Lots of errors. So those connections are too close. So I'm going to make this guy 30. Just iteratively playing with stuff to avoid getting errors. My X size is 40. I just want to pull this and make sure, yeah, it's that's not what I'm looking for. No errors. Copy and paste. And what I'm doing when I go over here and change the extensions to neither end is I'm just getting rid of a little bit of excess metal that was unnecessary. 2 errors. Let's see what's what here. Oh, I have an overlap for my, yeah. Which means let's pull this one out over here. Close that. This guy needs to be wider. So let's make it 45. Seems some Fedori.
Dr. Hartman,
Yes.
I don't think you connected that top one to the right side.
I didn't, but I usually only connect it on one side and it still works out fine.
Gotcha.
If I do connect it to both sides, I wind up getting weird pieces of metal that I don't want because it doesn't look neat to me. So that's why I didn't do it.
Gotcha.
But as long as it doesn't give me an error, everything is okay. And all right, so that's all good. I am simply just going to move these guys slightly so that things are symmetrical. All right, so that is my, that's the bit at the bottom. That's my NMOS transistor M1 and transistor M2. Let's see here. So why I'm herming is because I need to get my signals to and from this, right? Because input signal V in 1 is going to go to this guy, and input signal V in 2 is going to go to this guy, which means I'm going to need to run up to effectively metal 3 at some point. But I'm concerned. So if I were to put a contact here, I'm willing to bet I get, yep, lots and lots of errors. And if I try to run poly across this, I'd be willing to bet that I get errors as well. Yeah, so the poly and the metal one and all that kind of stuff. So what does that mean for me? What does that mean for me?
Could you just delete one of like the bottom part of the grounding ring and just scoot the entire like NMOS stuff down?
I could. So what you're suggesting is I delete that. So what I'm thinking about doing here. So let's see. If I tie this there, any error, 6 errors. Let's see. Oh, now it's giving me an error up here because these guys aren't connected because I made the connection with the thing that I deleted. So let me put that there. Move this guy over. And make my ends not extend so that I don't have that extra little bit of metal there. Press F5. Okay, all my errors are gone. Can I tie this guy here? Yes. No errors. All right, so that seems okay. So now I'm going to put a metal 2 to metal 1 connection. Tie them. Actually, I'm not going to do that just yet. So what I'm about to do might seem funny. My goal here. Let's see what error am I getting. My contacts are too close together. Still too close. Oh wait, I never hit F5. Okay. So why I made those contacts bigger is because I want to use a wider wire here. And it's purely just because I know that it's going to be effectively going to a bonding pad, so it's going to be long. So the wider I make it, the less squares it's going to have, and thus the less resistive it's going to be. So I'm just trying to think ahead a little bit on that end.
Could you make those like wider like you did the contacts for like the drains and stuff? Or does it have to be
I
like...
can. Let's see. Yep, I absolutely can do it that way. So that is a smarter way to do it. So let's delete these guys and do it this way. So let's make it 10 and the Y size. And now I'm going to have to drag it down. It's giving me an error because this guy is too close. So let's just delete that for right now and look at this. 0 errors. All right, let's do the same thing here. And right now it will give me an error because of overlaps and all that jazz. So we just slide it down and we're good to go. All right, let's throw one of these guys here, make it 4 by 8. Maybe 4 by 10. There we go. Yeah, so now I get both vias. Do the same thing on the other side. 4 by 10. Five errors. What errors are So it's saying that, let's see, metal 1 to metal 2 is less by 1/2 than 3 to that guy over there. So I'm making it 4 by 9, so it matches the exact size of the metal one underneath it. And that should get rid of that error. Yep, there we go. All right, so 4 by 9 is the size to go. And finally, I'm going to put a metal 3. And this guy is lower. Okay, I'm not going to put the metal 3 then because that's going to screw things up. I'll do the metal 3 outside of the ring. I have my metal connected. So, nope, I want metal 2. All right, so I'm just moving this chunk of metal to the outside of my ring. Let's see, let's make it 12. No, that's not what I wanted. I wanted the length. I'm just going to extend it like this. And I'm going to try to do the same thing over here. There we go. All right. So I'm still going to enclose my grounding ring, but now I'm just going to have to extend these guys. So let's make them 40 and slide it down. And no errors. Okay. So that looks good to me. Let's see. Those gate connections are fine. So my drain connection is going to have to go over that ground ring. So I'm going to do that on metal layer 2. So I'm going to make this a 4 by 9. Scooch this guy over and do another 4 by 9. that guy over. Oops. I need to connect them first and then do it. And so that should let me go over this. And no error still. Great. So I now have a way to get my drain connected to the drain of the Pmos transistors. Everything's looking pretty good so far. I do need to remember to connect my source to my body, which is done with metal 1.
Okay,
And
Dr.
this is
Hartman,
about to give me an error. Yes.
I'm confused at this point. Shouldn't the source be connected to a current source?
So the source is going to be connected to the current source, and it's also going to be connected to the body. Now, how we're going to get the source connected to the current source, how do we make an ideal current source? Let's talk about this. Oh, what the heck did I just do?
Wasn't there a way to use another transistor to create an ideal current source or something like that?
So ideal current sources, what?
Control Z, maybe?
Yeah. Where? Okay, there. Okay, I was freaking out. I was like, what the heck did I do? All right. No, that's not what I want. Sorry. I see that little piece of metal and it's bothering me. So you are, Aiden, you are correct that we can use a transistor as a current source, but we can't use it as an ideal current source because ideal current sources don't exist. Hold on just a second. I'm trying to find out why I have that via is too large. Okay, it was a residual thing from there. So, so to answer Grant's question, we're absolutely going to be connecting this thing to a current source. What we're going to be connecting it to is our current mirror that generates our reference current, right? That's why we made it. And we'll worry about how we're going to do that after we draw this whole shebang, and I'll show you guys a little something. Once I get this thing drawn in a way that's not ticking me off. There we go. So as a quick aside, I'm inside a schematic, right? Or inside this layout. I can go to Explorer and I can choose my Cascode layout and literally drop it in there. And it also imports all of my terminals and stuff like that. Now, you can't really see anything right now, except here's where VDD is, here's where VDS4 was, and here's where ground is. There is a way, I just have to remember view, make, that's not what I wanted. That's also, I don't want to see this there. I'll have to look at it. It's been a year since I've done it, but there's a way so we can make this layout, like you can actually see the layout of the NMOS of the devices that you drop into another layout so that we can wire up all the connections properly and all that kind of stuff. So that's what we're going to be doing. Looks like probably Tuesday, or not Tuesday, Thursday, because we only have 10 minutes left and we're only halfway done with this guy. And I also don't remember how to physically see the connections. Thought it was something easy.
Is it the C button?
So when I press C, press apply, it doesn't particularly do anything. What the heck is it? It's something to do. No. I don't know. We'll worry about that later. I'm just going to delete it. But yeah, we'll do that on Thursday. We'll get this guy connected up to our current mirror and then be able to run simulations on the full thing up to this point. But for now, I'm just going to focus on the differential.
I see the connections. It's just kind of in the middle of the block. It's kind of weird looking, but
yeah, so you can definitely see that. But I mean, what I'm saying is there's a way to actually see the layout so that we can run our wires strategically and make them wider and all that kind of stuff, because we're going to have longer runs, etc. Because at some point we're going to have to think about effectively doing a large power and ground bus.
I just figured it out. So if you select it and do Control I and then tick expand it, it'll show the whole thing.
All right. Select it, Control I. Oh, expand it. There we go. All right, so now, oh, that's not the one I wanted, but anyway. So we would want this guy. Drop it in, Control I, expand it, okay. And now we can see all this stuff. So effectively what we're gonna be doing is connecting where right here I have VDS4. This is effectively the output pin of the current mirror, and we're going to tie that to the grounding ring, and that's going to let us connect this guy to our current source. But like I said, for right now, I'm more concerned with finishing up the, let me just delete this guy, finishing up our differential input pair here. All right, so we got a couple of Pmos transistors. They're going to go up here at the top. So we go into components, Pmos. So these are going to be 30 by 2, and I'm going to do them as 3 10 by 2s in parallel like we did before. I'm going to rotate it 90. I'm going to call this guy M3A. Make it 1.5, rotated 90 degrees, apply. Move it down here. Set my spice level. Or spice model, sorry. Pmos. Rotated text 90 degrees. No, not Control I. Not that either. And I'm going to need to go through and right. P active. It's just saying that those two guys are too close to each other, which is fine because they're about to be connected together. It's telling me that that stub, it doesn't like it. I'm trying to think if I can. That's 3. All right. Over here. Alrighty, so based on, I think it was a Grant's suggestion last time, I think I'm going to run these gates serpentine, like so, because that will let me minimize my metal overlap. So the question becomes, do I want this guy to be drained or this guy to be drained? And let me think. Source is going to be tied up here to VDD. I'm going to make this guy my drain. No. No. Close together, move this back like that. All right. Actually, so let's see. All right, we're effectively out of time, so we'll finish this stuff up and play around with things, simulations, and all that jazz on Thursday. So if you want to continue working on it, by all means, feel free. If you want to wait till Thursday, you can do that too. Let's see. I'm just gonna hit F5. All righty. So it's 9:50. I don't know if you guys have other classes and all that kind of stuff, but I believe the polls close today at 8. So if you're registered to vote, and go do it and all that kind of jazz. I will catch you guys later.
Hey, Dr. Harmon, I had a quick question about senior design.
Sure.
Do we have the monthly team and self-evaluation form due today, or when are y'all going to make that due?
You can turn it into us on Friday at the Industrial Advisory Board workshop. And okay. I'm going to be sending out the information for that today. because we finally have everything finalized for where it's going to be, the timing, and all that jazz. So anything that was due today, just turn it in on Friday to me, and we'll call it good.
Okay, sounds good.
Alrighty. See you guys later.
Have a good one.
You too.